Hello everyone. Welcome back to our journey through geometry. Let me start with something interesting. Have you ever looked at a bicycle wheel or a coin and wondered what makes their edges so perfectly round? That perfect roundness is what we call a circle. Now, mathematically speaking, a circle is a set of all points in a plane that are at an equal distance from a fixed point. That fixed point is the center, usually denoted as O, and the equal distance is the radius, denoted as r. All the radii of a circle are equal. Whether you draw one from the top, bottom, or side, they'll always be the same length. A line segment passing through the center and touching the circle on both ends is called a diameter, written as d equals to r. So, if your radius is 5 centimeters, your diameter is 10 centimeters, simple double. Now, the total distance around the circle, or the circumference, is given by the formula c equals 2 pi r. So, for a circle with radius 7, the circumference would be 2 times pi times 7, which equals approximately 44 units. Interesting, isn't it? Every round object you see, from coins to clock faces, follows this very principle. Now that we know what a circle is, let's explore its elements, the lines and curves connected to it. A chord is a line segment joining any 2 points on the circle. If the chord happens to pass through the center, it becomes a diameter, the longest possible chord. Next, we have a secant, a line that cuts through the circle at 2 distinct points. Imagine slicing through an orange so the knife touches 2 points of the peel. Yes, that's a secant. A tangent, on the other hand, is a line that just touches the circle at one single point called the point of contact. If you've ever seen a car tire touching the road, that point of touch represents the tangent contact. A minor arc is the smaller part of the circle, corresponding to an angle less than 180 degrees. The major arc is the larger curve, greater than 180 degrees. And the area between a chord and its corresponding arc, that's called a segment. So, from chords to tangents, each part of a circle tells its own geometric story. Let's now look at how angles and arcs behave inside a circle. A central angle is formed when 2 radii meet at the center. For example, if you draw OA and OB, the angle formed at O, say AOB, is the central angle. Now, take 2 points A and B on the circle and join them to another point P on the circumference. The angle APB formed here is called an inscribed angle. Here's the fascinating relationship. The angle at the center is always twice the angle at the circumference for the same arc. That is, angle AOB equals 2 times angle APB. So, if the inscribed angle is 30 degrees, the central angle subtending the same arc will be 60 degrees. This property helps us solve many problems involving arcs, chords, and even cyclic quadrilaterals. Let's take it one step further. Imagine drawing several circles with the same center but different radii, just like the rings on a dartboard. Such circles are called concentric circles. Now, if 2 circles have the same radius but different centers, they are congruent circles, basically identical twins placed apart. For 2 concentric circles with radii R1 and R2, where R1 is less than R2, the region between them is called an annulus or a ring. The area of that ring is given by the formula equals pi into bracket R2 squared minus R1 squared bracket close. This formula is used when calculating the area of washers, donuts, or even pipe cross sections in engineering. So, concentric and congruent circles may sound similar. But remember, concentric share the same center. Congruent just share the same radius. Let's now talk about how a line can interact with a circle. Depending on where it's placed, a line can have 3 different relationships with a circle. Case 1. If the line doesn't touch the circle at all, it's a non-intersecting line. This happens when the perpendicular distance from the center to the line, let's call it OP, is greater than the radius. So, OP greater than R, no intersection. Case 2. If the line just touches the circle at one point, it becomes a tangent. Here, the perpendicular distance equals the radius. So, OP equals our case 3. If the line cuts the circle at 2 distinct points, it's a secant. That means OP less than R. So you can remember it like this: greater than R, outside; equal to R, just touches; less than R, cuts through. This simple relationship between line and circle helps in deriving many tangent and secant theorems later on. Now let's prove a beautiful geometric relation: the length of a tangent from an external point to a circle. Given a circle with center O and radius R, and an external point P outside the circle. A tangent from P touches the circle at T. We have to prove that PT squared equals OP squared minus R squared. Let's see how. In the right triangle OPT, we know that OT is perpendicular to PT because the radius is always perpendicular to the tangent at the point of contact. By Pythagoras' theorem, OP squared equals OT squared plus PT squared. Now substitute OT equals R. We get PT squared equals OP squared minus R squared. That's our required relation. This means the tangent length depends only on how far the external point is from the circle's center and the radius of the circle itself. Pretty neat, right? It's a formula you'll use repeatedly when we deal with two tangent problems and tangent secant theorems. So let's wrap this up. We began by defining a circle as all points equidistant from a center. We explored its basic parts: radius, diameter, chord, tangent, and secant. Then we studied how angles at the center and circumference are related. Remember, angle at the center equals 2 times the angle at the circumference. We also learned about concentric and congruent circles and found the area of an annulus as pi into bracket r2 squared minus r1 squared bracket close. Finally, we proved that the length of a tangent from an external point P is given by PT squared equals OP squared minus R squared. Understanding these fundamental circle properties lays the groundwork for the upcoming theorems, like the tangent secant theorem and properties of cyclic quadrilaterals. And that's the complete introduction to circles. In the next video, we'll dive deeper into tangents to a circle and uncover some fascinating geometric truths. Thank you for listening. See you in the next concept.